Hi students. In this lecture, I am going to discuss current electricity. First, let us see the list of concepts in this chapter. So, current density, drift velocity, then current density and drift velocity relation, Ohm's law. So, in that, we discuss relation between current density and electric field intensity, then calculation of resistance, then resistivity and resistance. How do they change with the temperature? Then battery and EMF. So in this we discuss energy transfer in the circuit. Next, thermal energy produced in the resistor. Then resistance of a battery. After that, relation between EMF and potential difference. Then Kirchhoff laws. Then resistors, series and parallel combination. Then Wheatstone's bridge. After that, combination of cells, series, parallel, then mixed grouping. Then we discuss electric instruments. So in that we discuss conversion of galvanometer into ammeter, voltmeter, and after that it is meter bridge. Then we discuss potentiometer. So in that we discuss comparing EMFs of two primary cells, then finding resistance of a cell, and finally we discuss color coding of resistors. So these are now list of concepts. Let us see first one. So how we define current. And before going to define current, first we define average current. Let us consider this is a conducting wire. So why we are taking a conductor means it contains large number of free electrons. Let us focus. Let us focus a cross section area. Let us focus now this cross section area. Now through this cross section, let us say in a time interval delta t, delta q charge is flowing. So delta Q charge is flowing. We can say this is net charge. Delta Q net charge is flowing through that cross section in a time interval delta t. Then average current. For current notation is I, and this is the notation for average value. Average current is defined as delta Q by delta T. This is definition of average current. So delta Q refers to net charge passing through a given cross section in a given time interval delta t. Okay. After having this average current, we define current. So it is defined as current equal to limit delta t tends to 0, delta q by delta t, which is equal to dq by dt. If you remember, this kind of language we have discussed in kinematics while discussing average velocity and velocity, right? And see how we are reading this as this is now the rate of flow of net charge. It is the rate of flow of net charge through a given cross section in a conductor. Okay, right. Now we will see why we are focusing their net charge. And before that, from this see what we can say. Unit of current. Unit of current. So charge means coulomb. and time is second. So coulomb per second, or this is known as ampere. So it is name of a scientist. So we are taking it is symbol is capital A. So that is now unit. And coming to here, dimension formula, it is m power 0, l power 0, t power 0, a power 1. So this is a fundamental quantity. Its meaning is it does not depend on other quantities like mass, length, time. So these are the fundamental quantities which are not depending on other quantities. In the same way, current also one of the seven fundamental quantities. It is not depending on other quantities, right? Okay. Now coming to here, we are defining direction of current. We are defining direction of current. That is, if you take dq is a positive charge, if dq charge flows right side, then direction of current also right side. That means direction of current, it is direction of flow of positive charge. I am repeating, direction of current is the direction of flow of positive charge. Or same thing we can say, it is opposite to the direction of flow of negative charge. Let us see carefully. Suppose this is now conducting wire. If you observe carefully the definition part, the rate of flow of net charge. So if you are taking conductors, they have large number of free electrons. That means metals which have large number of free electrons are good conductors of electric current. We can say examples like copper, silver, gold, right? These are some examples for good conductors of electricity because they have large number of free electrons. That means we can say insulators are not conductors of electric current because they do not contain free electrons. For example, in this conducting wire, you just assume atoms are moving, which are electrically neutral. So I am taking neutral atoms are moving. See what happens here. Since for this atom there is no net charge, there is no current in the conducting wire. There is no charge. There is no net charge for the atom. Therefore, even though atoms are moving, there is no current to flow. Okay. For example, if you are taking a chemical solution which contains positive ions and negative ions. If you assume that positive ions moving right side, then negative ions will move left side. According to our definition part, direction of current is the direction of motion of positive charge. That means because of this positive charges, current is now right side. I am taking here plus I plus because of positive charge. And if you see because of negative charge, negative ions, direction of current is opposite to the direction of motion of negative charges. Means again direction of current due to negative ions is right side. That means both currents are now right side. Therefore, current through that substance is sum of these two currents. Sum of these two currents. So students may have a confusion like plus and minus total value is negative. That is not correct. Because we can see here this atom which is neutral, which is a combination of plus and minus. So here atom moving right side means it is indirectly positive and negative both are moving in the same direction. So because of positive charge, direction of current is right side. Because of negative charge, current is, it is left side. I am repeating. Because of positive charge, current is right side. Because of negative charge, it is also moving right side, but direction of current is left side. So these two currents will now cancel. That means there is no current because there is no net charge. Okay. So the difference between these two, if it is clear, there is no confusion while solving problems. Right. Okay. Okay. Next, we can see one more thing here. From the definition part, we can say how much charge is flowing through a given cross section in a small time interval dt. That is dq equal to I into dt. dq is, it is a small amount of charge flowing through a given cross section in a small time interval dt. Now through that cross section, how much charge is flowing in a given time interval? Then we have to integrate, right? So this is giving us charge flowing in a given time interval. Okay. And if you see carefully, whenever we are taking integration, integration gives us area under the graph. So this is now I into dt. That means if you take current versus time graph, current time graph, then for example, graph is now passing through origin like this. Okay. Then this area with the time axis gives the net charge flowing in that given time interval. So which is more useful while solving problems. Okay. Right. Let us see one small problem here. Basing on this definition part, let us take electron which is revolving in circular path. Electron which is revolving in circular path around nucleus. So it's a charge. Take it as a q. It's a velocity, or you can say it's a speed. Speed is a constant. We want to calculate what is now equivalent current. So here charge is flowing. So because of this charge, what is the equivalent electric current? Then see what we are doing here. Since the speed is a constant, I am taking here directly q by in the place of delta t, time taken to complete one revolution, that is t, or it is equal to q by in the place of t 2 pi upon omega. So which is equal to q omega by 2 pi. Okay. So whenever a charge is revolving in circular path, because of its motion, the equivalent current is given by q omega by 2 pi. Or same thing we can say here, it is 1 by t, nothing but frequency. So q into f. So we can expect some easy problems, simple questions like this, basing on definition of current. Next, we can see one more thing here. Even though current is having direction, it is not a vector quantity. I will explain here why it is not a vector quantity. For example, this is one conducting wire, and here one more conducting wire like this, and one more like this. Suppose a current of 5 amperes is flowing towards right side. Let us say, let us say in this wire, current is given as 2 amperes. So this is now given 5 amperes and this is given as 2 amperes. Now what is the current in the other wire? What is current in the other wire? So you can see this is a 5 and this is 2. So remaining is now 3 ampere. And this value is not depending on the angle between these two wires. Okay. That means whatever may be the angle between these two wires, this current is always fixed. Once you are fixing this current, that means this 5 is always equal to 2 plus 3. It is not depending on this angle. So addition of these two currents, is not following the laws of vector addition. That's why even though current having direction, it is not a vector quantity. Okay. Let us see till now what we have discussed. So first we have discussed definition of average current. So chart delta Q crosses an area in a time delta t. Then average electric current is given by or defined as delta Q by delta t. Right. Next, the instantaneous current or simply current defined as limit delta t tends to 0 delta Q by delta t, which is equal to dq by dt, the rate of flow of net charge through a given cross section. Direction of current is direction of flow of positive charge, or you can say it is opposite to the flow of direction of negative charges. Next, coming to units, coulomb per second, or it is ampere. It is name of a scientist. That's why taking as capital A. So we are using only SI units. It is a fundamental quantity and dimensional formula is m power 0, L power 0, T power 0, A power 1. It is a scalar quantity even though it has direction because it does not obey the laws of vector addition. So these are the points till now we have discussed. Let us now solve problems basing on this to get clarity. Right, we have one more point, right? The area under the current time graph with the time axis gives the net charge that flows through a given cross section in a given time interval. Okay, right. Now see problems. See first one. An electron is revolving in circular orbit with an angular frequency 6.28 radian per second around the nucleus. Find the equivalent electric current. It's almost same kind of question just now we have discussed, right? Let us see once we are given 6.28 radian per second means omega is given. So omega is given. So given circular path, we have discussed that equivalent current is given by Q omega by 2 pi, right? Just put values in this Q value 1.6 minus 19, that is coulomb. Omega value 6.28 radian per second upon 2 pi. So these two gets cancelled. It is simply 1.6 minus 19 units are ampere. So very simple and direct question. See next one. An electron of mass m follows circular path of radius r around a nucleus and the centripetal force is given by the attractive force here. So nucleus is attracting electron, okay? That force is providing centripetal force. Find equivalent electric current. It's almost same question, but we have to get in terms of mass and this attractive force. That is the only change. Let us see where change comes. So we have discussed I equal to Q omega by 2 pi, right? Or since centripetal force given, I can write centripetal force is equal to m into centripetal acceleration is r omega square. Okay. From this, we get the value of omega. Omega equal to root of f upon mr, right? Directly. Now take this value in this one. Then we get the answer, right? Direct one. Okay. See next one. See the question carefully. The electric current in a conductor as a function of time is given as I equal to 2t plus 5 ampere. Find the amount of electric charge that flows through a given cross section of the conductor in the time interval t equal to 0 to 3 seconds. Also find in the same time interval average current. Okay. So we are given current as a function of time, asking how much charge flows in a given time interval, and also average current. See how we are going to solve this problem. Right. First, write down the given data. Current as a function of time, I equal to 2t plus 5 ampere. We have to find how much charge flows in the time interval t equal to 0 to t equal to 3 seconds, right? And also we have to find average current in the same time interval. So this is the data given, right? Okay. So first see how to calculate the charge that flows in this given time interval. So charge. So we have discussed that charge passing through a given cross section in a given time interval is given by I into dt, right? Integration of that. Now simply take value here 2t plus 5, that is given value into dt, limits 0 to 3. Very simple calculation. So 2t dt, it is a t square by 2. 2 gets cancelled. Remaining is t square plus 5t. Now take limits 0 to 3. See how much we get. 3 square 9. 9 plus 3 5s 15 minus 0. That is 24 coulomb, right? This is a charge flowing in that given time interval. Okay. And students, remember, since we have taken integration, the same thing we can do by taking area under the graph. Let us see how we take that. Solve the same thing by using area under the graph. Current versus time graph. This is a current and this is a time. This is now 2t plus 5, means having positive intercept and positive slope. So graph is now like this. Okay. Let us consider it is asking up to 0 to 3 seconds. When time t equal to 3 seconds, 3 seconds, we can see the corresponding current. So t value 3 seconds, 2 3s, 6, 6 plus 5, 11. This is 11 and this is a 5. Okay. It is an ampere. So now we have to calculate. We have to calculate area under the graph. We have to calculate now this area, right? This entire area. Or this can be taken as combination of rectangle and triangle. So area of rectangle is 3 into 5, area of rectangle. Area of triangle is half into base into height. Height equal to 11 minus 5, it is a 6. So height equal to 6. That is now charge flowing. Okay. So 2 here, 6, 3 times, 3, 3 is 9, 9 plus 15, it is 24. So we got same, right? So either we can calculate by using that current time graph by taking the area, otherwise take integration part. Okay, right. And here is asking now how much charge has flown. We got it. Next, we have to calculate average current. And you can see definition part, average current is given by how much charge has flown by time interval, right? It is now 24 coulomb. Time interval is of 3 seconds. So it is now 8 ampere. So it is very simple and direct one. And students, if you remember, whenever a function changes linearly, whenever a function changes linearly, then its average value is given by initial value plus final value by 2, right? We can solve in that way also. See what's initial value. When t equal to 0, current equal to 5. Initial value 5. Initial value plus when t equal to 3 seconds, current equal to 2, 3, 6. 6 plus 5, 11. So initial value plus final value by 2. Okay. So 5 plus 11, 16. 16 by 2, it is 8. Because current is not changing linearly. That's why average value is given by initial value plus final value by 2 directly. Either we can solve by using definition part like this or in this way also. Okay. Let us see next problem. See the question carefully. The electric charge flowing through a given cross section in a conductor as a function of time is given as 5t square plus 2t, given as 5t square plus 2t plus 11 coulomb. Okay. So we have to find electric current. We have to find electric current when t equal to 3 seconds, right? Next, we have to find average current in the time interval. Average current in the time interval 2 seconds to 4 seconds, right? Let us see how to calculate. In the previous question, we are given directly current, but now given it is charge. Okay. So first write down given data. Q equal to 5t square plus 2t plus 11. Okay. Given coulombs, we have to find the current when time t equal to 3 seconds, right? Next, we have to find average current. This is notation for average. Average current in the time interval t equal to 2 seconds to t equal to 4 seconds, right? Let us say first one, it is a very simple and direct one. I equal to rate of flow of net charge dq by dt derivative 5t squared is 10t plus 2, right? Now take in this one time t equal to 3, okay? So 10 3 is 30, 30 plus 2, 32, 32 ampere when t equal to 3 seconds. This is the current, right? Now we have to calculate average value. Coming to average value, since the current is now again changing linearly, what I can do is calculating initial value time t equal to 0, sorry, time t equal to 2 seconds. 20 plus 2, 22. Initial value plus final value. 10 into 4, 40. 40 plus 2, 42. Initial value plus final value by 2. See how much we get? 40 plus 20 is 60. So 64. 64 by 2. That is now 32. Okay. Cross check once. Since current is changing linearly, we can take average value as initial value plus final value by 2. Initial value. When t equal 2 seconds, 20 plus 2, 22. T equal to 4 seconds. So 40 plus 2, 42. Total is now 64. 64 by 2, 32 ampere. See, luckily here both are matching. Okay, na? In fact, they need not match. Right? Okay. Let us calculate same thing. In fact, we have discussed earlier using graph. We can try that also. And I will discuss a different way also. That is average value is given by delta Q, the net charge flowing in a given time interval. See once. So I'm taking here one cross section. Through that given cross section, when t equal to seconds, how much charge has flown? Okay, t equal to 2 seconds, how much charge has flown? So at that time, how much charge flowing means? Let us take it as Q1. See, t equal 2 seconds, how much? 5t square. T square 2, 2 square is 4. 4 5 is 20. 20. 20 plus 2. Right? Next, through same cross section, now how much charge is flowing when t equal to 4 seconds? It is t square 4 square 16. 16 fives 80. Wait. I have done mistake here. In Q1 calculation, 2 square 4. 4 fives 20. 20 plus 2 2s 4. 20 plus 4 plus 11. Okay, that is Q1. Coming to Q2, 4 square 16. 16 fives 80. 80 plus 80 plus 2 fours 8 plus 11. So when t equal 2 seconds, Q1 charge flowing. When t equal to 4 seconds, Q2 charge flowing. So how much net charge has flown? Net charge. Okay, now this is now 24 plus 11. This is 88 plus 11. Okay. Now see Q2 minus Q1. Q2 minus Q1 upon delta T. Delta T value how much? 2 to 4 seconds. It is 2. So 88 minus 24. It is a 4. This is now 6. So 64. 64 by 2. 32 amp. So like this also we can solve. So we can solve like this or we can solve. So method 1, you can say. This is method 2. Next one is by using graph. Okay, you can try that also by using graph. So in these three ways we can calculate average current. Okay.